So I'm going to continue the conversation from where Jeff left off on, challenges in accelerating transformers for inference applications at scale. Right? I think I'm the fifth person to put this kind of slide up. Jeff said he was the fourth. So this is a slide from Hardships where Cerebrus was showing that the growth of these NLP models. Right? So in the last 2 years, these NLP models have grown 1000x, 3x higher in complexity, in model parameters, in compute. Today it takes about four months on 1000 GPUs to train a model like GPT-3, and tomorrow that was sort of last year, and tomorrow it's going to be even trillion parameter and multi-trillion parameter models. So the question then is, how do you actually do inference at scale on these very large models? So there's a crisis in terms of serving NLP at scale. This is some data from MLPerf. So MLPerf, does this benchmarking. More recently, they've added power consumption to these benchmarking experiments, and this is what it takes to serve BERT large, right? On DGX A100, the NVIDIA boxes. So we can see somewhere between 6 to 8 queries per second per watt for BERT large inference, right? So how, if the throughput and the efficiency is so low, how do we serve these models that are now 3 orders of magnitude higher in terms of parameters? Will it take 1000 GPUs to serve 8 queries? So none of the promises that Jeff mentioned before is going to really translate if it consumes that much power. So I'm going to talk a little more about that, get into the details a bit. So let's dive into what a transformer is, right? So everything is built up of these transformers, and a single transformer layer block diagram is shown below. At the end of the day, a model like BERT large has really, about 4 parameters. There is the sequence length, which is a number of tokens that Jeff talked about, the efficient tokenizer library. So you pad everything up to 384, at least in the MLPerf benchmarking cases, and there's an attention head, which is in the BERT large case there are 16 such attention heads. There are 24 layers of this model and an embedding width of 1024, right? And variations of these parameters are used to build pretty much all these transformer models today. So at the guts of it, from the attention is all you need paper that Jeff showed before, you have essentially a computation of attention scores, right? So what you're trying to do is measure the probability distribution and come up with a numerical value at the end of the attention based on the context of all the words around it. So to quote the NLP professors, a word is known by the company it keeps. So you want to compute different combinations of a softmax around the particular input value, and so that's shown in this equation here. It's a softmax on QKT transpose, and that provides a probability distribution around the value matrix output. So you have this large matrices multiplying the embedding layer. You have multi heads, 16 of them in BERT large case, and then you have some more transformations going on before you can compute softmax, like a transpose operation. And then once you compute the attention score, that's where you start getting into these 3 different fully connected matrices to mix up, first of all of the attention heads together, which is this first FC matrix. and then that goes through a shortcut connection, a local response normalization block, and then finally 2 FC layers and a GALU activation function between them. So so this on BERT large takes 5.6 gigamax per transformer layer. So it's a very computationally intensive layer. To give you a sense, ResNet 50 is around 3.8 to 4 gigamax for the whole network, for all of the 50 layers. So a single BERT large attention layer of this size is of the order of the entire ResNet 50 workload. So so that and then the trillion parameter NLP models that people are building today essentially is just a scale up of those parameters. So the way to get to trillion parameters is to vary the attention heads, go from 24 attention heads to 160 attention heads, to vary the hidden dimension, and also the number of layers. And so with just scale up of those 3 parameters, you can get a trillion parameters. You can see what GPT-3 did here. So GPT-3 there's a family of models. So the largest one, the sort of the GPT-3 that everybody refers to, is the 175 billion parameter. It's got 96 layers. It has a embedding width of 12,288, and there are 96 attention heads in that model. And this parameter is just a division of these 2 parameters. And then you can also see GPT-2 doing exactly the same thing. So that's the way people build these transformers, and so the bottom line is that these transformer-based NLP requires very high compute. In the GPT-3 case, this is a chart from Microsoft. It's 90,000 times ResNet 50, right? So it's 5 orders of magnitude higher. So one of the challenges then at inference is to deliver this kind of performance at the lowest energy consumption. And Jeff talked quite a bit about this. Quantization and sparsity is something that you can use. Knowledge distillation is something you can use. Of course, efficient tokenization and various techniques at the software layer is another thing that you can use. Now, one of the things that you can also use is to support variable sequence lengths. We don't need to pad everything to the highest sequence length, 384 or 2K or whatever the model claims. There's generally a distribution to the sequence length depending on what you're seeing. If it is short text, the sequence length may be even 20 words, 20 tokens, or it could be entire paragraphs. So if you can support variable sequence length in the hardware architecture, that's going to be much more efficient. Then the challenges then are, how to split the self-attention among slices and chips, and the performance is impacted by many different things. One of the things is that the softmax tends to be in the critical path of these transformer layers because it's computing the probability distribution, and traditionally softmax hasn't been accelerated very well in hardware. So in layers like these, in models, workloads like these, softmax can become the bottleneck. So you have to pay attention to that. We have to overlap the compute, the various SIMD operations that are happening, and the knock transfers, and efficiently utilize both the memory bandwidth and the communications and the compute. So I'm going to dive a little bit deeper into maybe a couple of topics here, specifically around quantization and sparsity. So of course we can use integer quantization. Unfortunately, most of these networks don't go through training with integer quantization in mind. They don't adopt quantization over training. They're just trained in floating point. And at the end of the day, when you want to do inference with integers to get better efficiency, you start seeing a lot of hand tuning that is needed. And this is what happens in TensorRT in the NVIDIA libraries, software SDKs. You have a choice of many methods, and it is not clear a priori which method works well, right? It's a lot of empirical hand tuning. Some results are shown here. So for computer vision networks like ResNet and networks like that, the entropy-based methods looking at KL divergence works pretty well. So you start to see the scores matching the top one scores, matching the FP32 trained results. But when you go to more efficient networks like efficient net, and certainly for NLP networks, these entropy-based methods, just don't work at all. I mean, the accuracy drops to 37% from 91%. And then, TensorRT does provide, two other types of calibration procedures, a max calibration procedure, which can be used to tune the scale factors, and that that also doesn't work very well. It drops by about 6%. And then finally, there's something based on percentile, and then you can of course choose the percentile. And then you have this huge amount of percentiles that you can choose, and as you can see, 99.9% doesn't work very well. You got to go to 3 nines before you start to recover the accuracy. So there's a lot of hand tuning involved here. It is not clear when you start this process, whether this will actually work. So can we do better? So there's been a lot of research from Microsoft around block floating point numerics and using block floating point numerics, what Microsoft calls MSFP, to alleviate some of the pain points of these sort of problems. So I'll briefly talk about that. So training is generally done in FP32 or more recently block float 16. And then inference, people want to do int8, and we just saw the challenges of using int8. The idea with block floating point is that you share an exponent across a number of mantissa or significant values, right? So as opposed to floating point where you have a separate exponent per mantissa, you share an exponent across a set of a vector of values, and that works very well. Because you can get the efficiencies a fixed point without having all of the problems of integer arithmetic. Furthermore, it works very well also because you can use smaller mantissas like a int4 mantissa with an exponent, and the network seems to retain its accuracy. That is shown in this paper below. This is the Microsoft paper. And for example, for the NLP workloads, what you see is that the MSFP12, which is just a 4-bit mantissa, retains its accuracy while of course getting the memory density and the arithmetic intensity to be a fraction of floating point, 32x better. So we looked at that, and so we've been looking at 3 different technologies to accelerate inference at d-Matrix, and they are basically trying to combine the multiply accumulates within the memory, various forms of in-memory compute technology, and also trying to combine the numerics and the sparsity, the block-based sparsity, and the mapping algorithms around the digital in-memory compute. So trying to harden these things inside the IMC. Finally, as these models get so big, it's almost impossible to fit it all in one chip. So you have to come up with ways to scale out these chips. They'll probably not fit within a reticle sized. So there is an effort from Facebook in Open Compute called the called the ODSA, the Open Domain Specific Accelerator project, and they're trying to define interconnects for chiplets on organic interposers. So that is something that we are also adopting and driving. So we can use these three techniques to improve the computational efficiency and bring the inferences per second per watt of NLP networks to something that is more manageable and that can be deployed at scale. So let me talk a little bit about that. So all of the training today is, of course, done with, say, NVIDIA GPU. For example, here, there's dense FP16 activation, dense FP16 weights, and FP30 accumulation. So by using block floating point 16 for the activation, block floating point 12 for the weights, and and our sparsity, we can accelerate the inference of these trained models and get much better performance. So we call this efficient algorithm co-design, and we're trying to optimize that for Corsair, which is the product we're trying to build. So we tried this on many networks. So BFP 1664 shares the exponent across 64 values. What we find is that if you have already a trained networks in floating point, Jeff mentioned about it takes three engineers to man-months to train and fine-tune all of these things. But block floating point 16 without much fine-tuning can actually retain the accuracy while preserving the original network's accuracy and accelerating the throughput of them. So we tested this on many models, Cipher 10, Cipher 100 datasets, ImageNets, as well as MRPC, MNLI, and Squad. And this works surprisingly well and without any fine-tuning, without any calibration, without those three things I showed with TensorRT, we are able to use these sort of data formats and improve performance. So this is a chart of what we can achieve. So the top line here is FP32 accuracy on ResNet 20 on Cipher 10, a small network, and we're able to get 92.6% accuracy on networks that are on formats that are lower precision than that. For example, the weight is block floating point 12, which is a 8-bit exponent, 4-bit mantissa. The network accuracy drops. But with some, even 1 or 2 epochs of fine training, we can completely recover that. And that also applies for sparsity. And these are 50% and 75% block sparsity that Jeff described, and subsets of them. And based on that, we are able to completely recover based on fine tuning. So we have a procedure here where, with very little manual intervention, we can even exceed the performance of FP32 with this block floating point, and then recover most of the accuracy drops with a couple of epochs of fine tuning. And this is on BERT base on MRPC, so an NLP workload. We see similar trends. The block floating point 16 and sharing the exponent over 64 values retains the performance, but you need to do some amount of fine tuning to use more energy efficient formats. The sparsity is still work in progress. We hope to have those results soon. So that is some of the techniques we're using. I'll talk a little bit about the silicon that we have built so far. So we built a silicon, a Nighthawk. We call it a Nighthawk proof of concept chip. That particular chip is a TSMC 6 nanometer silicon. It's a small 10 millimeter square proof of concept chip. And what we did on that is to have 4 neural cores. Each neural core has these compute cores called the octal compute core, where we have the in-memory compute modules. We have 8 of them, hence the octal compute core, hence the name, the octal compute core. And these 8 in-memory compute cores does the matrix multiplications. The octal compute core also has an element-wise SIMD unit, a vector SIMD unit that is programmable. And the weights are stored locally in the octal compute core, so it's weight stationary. And then the NOC connects up all of these 4 cores. It's able to multicast the input activations to all of the cores, and after the compute is done, it's able to collect the partials and unicast the partials for a spatially distributed accumulation. So this is the prototype we built. We have a control processor, which is a Sci-Fi RISC-V CPU. So we looked at a number of variants for the CPU to control these cores. What we found is that the RISC-V CPUs have an open ISA, it's extensible, and and also it has a very stable tool chain, right? It comes with assemblers and simulators and compilers. So we were able to develop this fairly quickly with this tool chain. So we were able to get a whole software stack running on this proof of concept chip. We were able to express the workloads in PyTorch, export them to Onyx, and use a spatial mapper to take the Onyx graph and map it spatially and temporally across all of the 4 cores. And this mapping process happens in the host and dumps out a RISC-V binary. And then the binary is then interpreted and executed by the RISC-V CPU. And the chip also has 4 die-to-die I/O interfaces, so you can put it together as chiplets or use the die-to-die I/O to connect up to an FPGA host. So it's a picture of an experimental setup with that chip. This is the top picture is a picture of our labs in Cupertino, and this is our eval board with the chip. And in the bottom here we have our eval board connected to an FPGA, and the FPGA hosts a PCI connection because the test chip is small and we don't have peripheral I/O on that. And the die-to-die I/O is used to talk through an HMC connector to a Xilinx FPGA, and the host has a PCIe cable here connecting to the FPGA. So we're able to start PyTorch and then come in and through the PCIe and start the demo and bring up of the test chip silicon on this platform. Check how we're doing on time. So still have 5 minutes. So what we have from a software perspective is we have an intermediate representation that takes the Onyx graph, expresses them in a way that can also express the new numerics, for example, the block floating point numerics or the sparsity patterns. And once the IR is spit out by the top of the compiler chain, the spatial mapper breaks that into a dependency graph. The pink boxes here are the matmul, the green are the load instructions, and so on, and that is scheduled on the RISC-V. So we were able to bring up this test chip fairly quickly. We had silicon back in February timeframe, and we were able to compile a graph, bring it up on the silicon, and get the entire software stack running by the May timeframe. Now we have sufficient confidence to go build a product based on that, and this is the product we want to build. We want to scale up that test structure, put a lot more cores, build a larger chiplet, and put many chiplets on an organic interposer. And as you guys saw, there's a huge growth in the size of the NLP model. So we're using LPDDR as an interface to connect to this Corsair chiplets. There are 2 LPDDR chips per chiplet, 4 channels of 16-bit LPDDR, and we're able to get a lot of memory bandwidth, memory capacity using a lot of different DRAM channels because of the in-memory compute nature of the compute happening. Most of the weights within a layer are kept in the IMC layer, and we minimize data movement energy and get very high energy efficiency. So we are able to, because of that, deliver 6.4 petaops on a single PCIe card at 175 watts. So about an order of magnitude better than what is out there today. And we have different SKUs of this. We are trying to target markets all the way from 5G infrastructure edge to autonomous vehicles to cloud. And so we can have a one chiplet configuration or multi-chiplet configuration in various PCIe card form factors. So this is something that we are working to building. And that is my last slide. Thank you. We are hiring across the stack. So if any of you are interested to work on these problems, from machine learning research to hardware architecture to software, please send me an email.
Thank you, Sudeep, for lighting talk. We already have a couple of questions on the queue. So Mustafa.
Hi, Sudeep. Thanks for the presentation. So could you elaborate more on the IMC technology you adopted, whether it's digital or analog, and if it's digital, how efficient it is compared to normal digital compute?
Yes. So we went through an extensive prototyping process. So the first question, Mustafa, is what kind of memory technology should we pick? Should we pick non-volatile memory technology for the in-memory compute? Should we pick something different? So we looked at non-volatile memory, flash memory, RMs, and so on. And what we found was that for the applications we're going after for large NLP models, having a completely weight stationary spatial architecture it doesn't really work very well because the model size is just too large. And the amount of time it takes to swap in new models is too much. So we ended up using an SRAM-based in-memory compute architecture. And so we don't store 8-bit weights like other flash memory architectures out there. We store 1 bit at a time. So it's more digital in nature compared to DACs and storing 8-bit weights. As far as a question, so it's much more efficient in terms of data movement because we obviously store all of the weights inside the IMC and we don't need to swap it as often. An entire attention layer, for example, can be done with the weight stored right in there. So we are about, when you include the numerics and the sparsity into the IMC, we are about 10x 40 tops per watt type of metric compared to 4 to 5 tops per watt on traditional digital architectures.
Thank you. I think we have one more question, and I think we might have time for that last question. Ayush?
Hi, Sudeep. Thanks for the great talk. So I wanted to get your comments on how do you think, so when we compare, let's say, a digital in-memory versus a digital non-in-memory like NVIDIA Tensor Cores, how do you think is the technology scaling of these newer technology look like compared to, for example, existing Tensor Cores have scaled down to 5 nanometer and probably there's a roadmap for further. So from the technology scaling perspective, does in-memory offer a favorable roadmap?
Yeah, that's a great question. So the short answer is for the digital in-memory compute, it does. We don't use any extra steps. We use the traditional TSMC PDK and the toolkits, and we are able to scale down along with the process nodes. So we are able to scale down to 5 nanometers and 3 nanometers and so on. If you use non-volatile types, there's a real problem there because most of them are in today NOR flash is in 28 nanometer node, so there is no real roadmap there to scale it down. But with SRAM-based digital in-memory compute architectures, there is a clear roadmap to scaling them to 5 and 3 nanometer.
Thank you, Sudeep. Again, thank you for the talk. This was very enlightening. If there's any other question, please put it in the chat. We are running out of time, so I will move on to the next speaker. Thank you again, Sudeep.
Thank you.